Hey everyone, welcome back, and today let's solve Leetcode problem 1298 titled Maximum Candies We Can Get from Boxes. So to kind of just quickly summarize what the problem statement really is, we're given several different input parameters, several different boxes if you will. They each have a status, either open or closed, or 1 or 0, and they each have a number of candies. They each also contain keys to other boxes, and other boxes contained within the boxes, right? So effectively we start kind of our journey or input with some initial boxes, and our goal is to actually collect or maximize the amount of candies that we actually obtain or collect. And the way we can do that is opening boxes if we have the key to them, or if we've already opened them, or if they're already open, and collecting candies from those open boxes. And we then use the keys that we found from those boxes to open more boxes and explore those contained boxes for more and more candies to maximize the number of candies that we do kind of obtain, right? So let's go ahead and look at the examples really quick here, just to quickly kind of just gloss over how they're really structured. So we're given 4 different parameters more specifically: status to check if each box is initially open or closed, the number of candies each box contains, the keys of basically which boxes contain the keys to which boxes, and the contained boxes, right? Which means really which boxes contain which boxes keys, right? So and finally, of course, we have initial boxes as well, which is the number of boxes that we actually start off with, which is just box 0, right? We're initially given rather just box 0, so we only have one option to even open from. That's just that 0th box, and in that we'd find 7 candies, because candies at index 0 or box at index 0 is 7. And so we get 7 candies from box 0, and then we'd open boxes 1 and 2. Why? Because contained boxes at index 0, again, the index 0 because this is box 0, that has 1, 2, and so we'd open or get the key for boxes 1 and 2, right? Or rather, we get boxes 1 and 2, right? But we know box 1 is closed, and we don't have a key just yet for box 2, but we know we can find 4 candies and a key to box 1 in box 2, and then we can kind of go from there to maximize our candy of 16, right? Again, very simple, straightforward structure again. In this case, our maximum is 6. We only have one initial box still, it's just box 0. But if we open it, we can find the boxes 1, 2, 3, 4, and 5 and their corresponding keys. And so with the number of candies we can get in total would just really be 6, meaning just all the candies from all the boxes, which is just 1 plus 1 plus 1 plus 1 plus 1 plus 1, or 6 in total. So for the constraints here, we see that n is going to be the length of our status, which is also equal to the length of our number of candies we have, also the number of keys we have, and the length of the contained boxes. And that value n, or that length n, is going to be between 1 and 1000, where any status at index I is always guaranteed to be binary, meaning either 0 or 1. It's either always going to be closed or open. There's no middle value, if you will. And any values in the candies array is going to be between 1 and 1000. The length of our keys is going to be always between 0 and n. Any value in the keys is going to be between 0 and n as well. All the values in the key are going to be unique, and yeah, just a bunch of different parameters, if you will. If you want to read this, really all they do is just confirm what the problem statement said, and kind of just tell us that we're always going to have valid inputs, if you will. Which brings us to how do we really solve this problem, and what is the main structure of this problem? Now, when you really look at this problem in nature, it kind of just resembles innately a graph traversal kind of method here, right? Basically, we can consider each box to be one node, or different boxes to be different nodes, and the keys would kind of represent edges to other boxes, kind of connecting them, because if we have the key to boxes, only then can we kind of traverse them or go to open them, right? And so for key observations to make, again, this is kind of in nature a graph problem. We do have edges, we do have nodes of boxes, and so what's a very standard graph algorithm? Well, it's going to be the breadth first search, or BFS algorithm, right? Because of course we have to explore the boxes level by level when we actually get keys for them, and we also need to track in this BFS the amount of, or which boxes we've opened, which keys for boxes that we found, and all the boxes that we've encountered but we still can't open yet because we don't have the corresponding keys for them. Right now, how is BFS typically structured here? Usually we'll have a queue to perform the BFS to contain all the different nodes that we get that we have to operate on. We'll have a set to track the keys that we have. We'll have another set to track the boxes that we have opened, and we'll have a final set to track the boxes that we've encountered, but again, don't have keys to open yet. We can't open them yet, if you will, right? So let's go ahead and get into the solution here. And like I was talking about, we have to actually initialize those sets, but before that, usually what I do for problems is I always just grab the length of our input, whether it be an array or whatnot, and I just get it sort and add. In this case, we're going to get the length of status, which is actually going to be, well, the number of total boxes that we have, and we're just going to store that in and to help iterate over it and initialize our other variables and data structures in a more easier fashion without having to actually iterate over the length of the status each time that we do that, right? Now, once we actually do that and determine the number of total boxes we have, now let's actually initialize those three sets to keep track of what we were talking about before. It's going to be visited, it's going to be have keys, and I'll try to make these as kind of intuitive as possible, and it's going to have waiting boxes, and they're all going to be initialized initially to empty sets. And again, to kind of just quickly reiterate the point of these boxes, or these sets rather, visited is going to keep track of the boxes that we've opened so far. The have keys is going to kind of store the keys that we found so far, and the waiting box is going to be the box that we've encountered so far, but we can't open yet. Now, we always, or rather typically need a queue for BFS operations when we're applying operations on nodes and processing them, and this problem is no different. Let's initialize a queue, and initially it's just going to be an empty double-ended queue, or DQ in Python, which is going to be used for that BFS solution. Now, to actually kind of have that pre-processing or building, if you will, for the queue here, we have to process our initial boxes. How do we get our initial boxes? We kind of start off from that we initialize our queue with to build off of there for future iterations of the BFS level by level. Well, to actually start off with these initial boxes, we really just have to iterate over our initial boxes input, right? And so to do that, very straightforwardly, we'll have for every box in the initial boxes that we have. I believe B was capitalized. Yeah, B should be capitalized. Right, basically just going through each initial box that we're starting off with. If status at that box, if status at box is equal to 1, and again, recall that if status at box is equal to 1, there should be equal, that means it is indeed open, right? Status at any box equaling to 1 means it is open. I don't recall where exactly they say that. Right here is 1 if it's open, or 0 if it's closed, right? So if a current box that we're initially starting off with, if it's open, well, then we want to continue it, or rather add it to process onto our queue for the BFS. So add to the queue the box, and add to visited, of course, as well, the box, because of course we're quite literally visiting this box in this iteration here. However, if it's not, that means guess what, we have the box but we can't actually open it yet, and so very straightforwardly we append it to waiting boxes. Waiting boxes dot append. In this case, I'm going to be appending, well, you guys did the current box that we're iterating over for each box that we initially start off with, right? Again, to kind of quickly reiterate, basically, really all this is just a pre-initialization, or the processing part, where we actually process the initial boxes that we start off with. So if they're open, we add them to the queue in the visited set. If they're closed, we simply add them to the waiting set, right? Very straightforwardly. Now, once we actually get through this iteration here, let's actually initialize the total candies that we have. And this is basically just the total candies that we've collected so far. Also, it's going to be kind of what we return. Why? Because we're trying to return or maximize the number of total candies that we can collect from all the different boxes, right? So that's going to be the total candies that we've initialized or encountered so far in each iteration, and it's going to be initially set to 0, right? Because initially, well, we don't collect any candies, right? Now, for the main while loop of our DFS, or rather our BFS solution here, while queue is non-null. That really means while we still have nodes, or in this case, while we still have boxes to process, that's stored in our queue, we'll keep going with the BFS level by level operations and iterations, if you will. And a very common structure of BFS is we pop off first the current box that we're actually processing, which is going to be queue.popLeft. And I'm just going to call that current, or you can say current box or current node, if you will, really just to get or extract the next box that we have to process in this iteration here. And the first thing that we have to do is actually collect the candies from this box. So total candies is going to be plus equals candies at this current box. The number of candies that we have in the current box that we can get from candies array, we're just adding that to the total candies that we've collected, because we've collected that many more candies from the current box to our total candies collected so far. Now we have to actually process the keys that we found from this new box. So for every single key in keys in the current box, this is going to tell us which boxes the current box has a key to, right, to actually see if we've found any new keys for any new boxes. So for every key in that value here, if key is not in have keys, meaning, you guessed it, we don't have the key for this current box that this box has a key for just yet, well, then we want to add it to our have keys set. So have keys dot add the current key that's part of this box. And if this key is in waiting boxes, meaning it was previously closed, right, that we saw in the initial boxes here. Well, then what we're going to do is we're going to add to our queue, so queue.append the key. We're then going to add to visited box. Was it visited or visited boxes? Just quickly. Okay, it was visited.add the current key as well. And finally, we're going to add to waiting boxes as well. Remove the key from waiting boxes. Now, how exactly does this initial iteration or this initial for loop work? Well, effectively, we're just processing the keys that we found in this new current box, right? We're adding the new keys, the new keys to the have keys set, and if any waiting boxes can now be opened with these keys, we then move them to the queue and remove them from our waiting boxes. Because of course, if we can actually open them with the new key, then there's no point of them being in waited boxes because they're no longer waiting. We can now process or open them, and so we're going to add them to the processed or available boxes to our queue and our visited set and remove them from the waiting boxes set if we can actually open them with the keys that we found in the current box. Now, we're going to have one more iteration here to process our contained boxes, because again, note that it has each box has two properties. One that contains the keys for other boxes, and then the actual different boxes it contains itself, right? So for every box in contained boxes, in this case now, at the current box, right now all the boxes that this current box actually contains, if the current box that we're iterating over, the box that we're iterating over in this current box, if it's not in visited, we haven't seen this box just quite yet, in that case, if it's open, meaning if status at box, if that's equal to 1, meaning again it's opened, or the current box is in have keys, meaning you guessed that we have a key for this box from previous iterations, well then we can still, same thing, add to our queue or queue.append the current box, because it is an available box. We have the key for it, or it is indeed open, right? And so we can add it then also to our visited set for this box. However, if neither of these conditions are true, the current box that we're iterating over and our current box that we're iterating over the outer loop here, if basically, again, current is the current box that we're iterating over. If any box in this current box itself is indeed open, meaning it has a status of 1, or it's in keys that we already have from previous iterations, we can add it to our visited and queue available nodes or boxes. However, if that's not the case, well then we have to add it, you guessed it, to our waiting boxes that we can't quite open yet. So add the current box, right? Again, we're just processing the contained boxes for this current node. If we can open them, we add them to the queue and the visited set. Otherwise, we just add them to waiting, right? And finally, really all we have to do once this while loop is actually done iterating, once we actually process all the nodes or all the boxes, we just return total candies, because it would eventually be the total candies collected after we process all our boxes, right? So unless I made any syntax errors here, there should be accepted and there should be a valid solution. And let me just kind of zoom out for you guys to kind of see the overall code here. It is quite lengthy code, and usually graph algorithms and BFS or DFS solutions are this lengthy. Okay, let's see. Yeah, so this should be add rather than append. Sorry about that. Simple error there. I might have made another very silly mistake, but other than that, this should be accepted and it should be valid. And as you can see, this really is just about as efficient as you can get it to be. It really is, the most efficient solution there is, right? So again, to kind of reiterate on a high level how we're really solving this problem, effectively we're just performing that BFS kind of iteration or algorithm, starting from the initial boxes and building off from there layer by layer or iteration by iteration. And we're collecting the candies from boxes that we can actually open. We're then gathering the keys from the current box, or rather in each box. We're then using those keys to open more boxes in future iterations and continuing that process until we can't actually open any more boxes, right? So that brings us to the complexity of this solution. For the runtime complexity, it is really just linear big O of n, and it's going to be the number of boxes. Why? Because at the end of the day, we really just process each box exactly once in our while loop here, and we can say the same thing, fully simplified for our memory or space complexity as well. That's also big O of n for the sets and the queue that we use to track the state of all the different boxes and the total candies that we've collected from them. And really, if we simplify it, it's going to be big O of n. Technically, we do have some coefficients in there, like big O of 4n, but that doesn't matter. It's really just linear as well, just like the runtime complexity of a fully simplified big O of n, because coefficients and constants, again, don't matter in runtime and space complexities. So if you guys enjoyed the solution and learned something new, please consider liking this video and subscribing to my channel. And without further ado, I will see you guys in the next video. Bye-bye.